Hello, in this lecture I will answer two questions. In the first question, we'll find out the area of this green triangle, triangle ABC. And in the second question, we'll find out the length of this short line segment AP that is equal to x. We have to find out the value of x. So let's start with the first question. In the drawing, we have the big quadrilateral QABCP. It is given as the question that AQ equals to AC. Therefore, triangle QAC is an isosceles triangle, and QC is the base of the isosceles triangle, triangle QAC. In addition, it is given as the question that this is angle PQC, that is right angle. This is angle QPC, that is equals to 60 degrees in size. This is angle ABC, that is also equals to 60 degrees in size. This is line segment PC, that is equals to 4 units in its length, and this is side AB, that is equals to 5 units in its length. Again, our task is to find out the area of this green triangle, triangle ABC. So, first of all, we will do a construction. That is to say, from point A, we will draw perpendicular on the base QC of the associated triangle, triangle QAC. Repeat again. From point A, we will draw perpendicular on the base QC of this associated triangle, triangle QAC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A in the base QC. This point is point M. So triangle QAC is an isosceles triangle, and we do the perpendicular AM to the base QC of this isosceles triangle, triangle QAC. So here we can implement rule 5. Repeat rule 22. I'll repeat quickly on rule 22. According to rule 22, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have triangle ABC, that is an isosceles triangle because side AB equals to side AC. The base of this isosceles triangle is BC. So from point A, we drew the perpendicular AM to the base BC of this isosceles triangle, triangle ABC. And according to this rule 22, the perpendicular AM to the base BC bisect the base BC. That is to say, the perpendicular AM divides the base BC into two halves. The first half is BM and the second half is MC. And of course, the first half BM is equal to the second half MC. So BM equals to MC. So we can implement rule 22 in our drawing. Why? Because in our drawing we have the isosceles triangle, triangle QAC. From point A, we draw perpendicular AM to the base QC. Again, from point A, we draw perpendicular AM to the base QC of the isosceles triangle, triangle QAC. And therefore, according to rule 22, the perpendicular AM to the base QC bisects the base QC. That is to say, it divides the base QC into two halves. The first half is QM and the second half is MC. And of course, the first half QM is equal to the second half MC. So if we define the length of the first half QM as A, then the length of the second half MC must be also equal to A units in its length because they are equal to each other according to rule 22. In the next step, we will extend the perpendicular AM by straight line until it touches line 7 PC. Repeat again, we will extend the perpendicular AM by straight line until it touches line 7 PC. And we will define the touching point of the extended perpendicular AM with line 7 PC. This point is point N. AM is a perpendicular, it is absolutely a straight line. We extended the straight line AM by straight line and the result is AN. When you extend the straight line by straight line, the result must be a straight line. Therefore, AN is also a straight line. If we focus on the right side of the straight line AN at point M, here the sum of the angles must be, if we focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? You have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the big right triangle PQC, 90 degrees plus 60 degrees is 150 degrees. 150 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle M and C, 30 degrees, 90 degrees plus 30 degrees is 120 degrees. So 120 degrees plus the size of this missing angle, in total they must be equal to 180 degrees according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size. It is very easy to see that the big right triangle PQC is similar to the small right triangle NMC according to angle similarity rule. I will prove anyway why the big right triangle PQC is similar to the small right triangle NMC. First of all, this is angle C that is equals to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. So we can write down that angle C is a common angle that belongs to angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So if we prove that all the three angles of the big right triangle PQC are corresponding equal to all the angles of this small right triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle PQC is similar. This is the sign of similar to the small right triangle NMC. According to angle similarity rule. And from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. Repeat again from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. Over PC, it is given us the question that PC equals to 4 units in its length. And it is equal to MC. MC equals to A units in its length according to our definition. Over QC. QC in total equals to A plus A, that is 2A. So in total we found out that NC over 4 equals to A over 2A. So we have A in the numerator and A in the denominator, so A will get cancelled. So in this order of the question we left only with 1/2. That this is equal to NC over 4. So in total NC over 4 equals to 1/2. Here we will multiply this equation by 4. And we get that the missing side NC is equal to 4 over 2, that is 2. So if we found out that this is the missing side NC, that equals to 2 units in its length. In the next step, I'm copying the big triangle A and B in a new page, and we will analyze this big triangle A and B. So actually, this is the big triangle A and B that are coming from the original drawing. Side AB equals to 5 units in its length according to what is given as the question. 60 degrees plus 60 degrees is 120 degrees. So 120 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore this third missing angle must be equal to 60 degrees in its size. All the angles in triangle A and B, they are equal to each other, and therefore triangle A and B is an equilateral triangle. So write it down. Triangle A and B is an equilateral triangle. You know that all the sides of any equilateral triangle are equal to each other. AB equals to 5, therefore AN must be also equal to 5 units in its length. NB must be also equal to 5 units in its length. So actually, this is side A and B of the equilateral triangle, triangle A and B, and it is equal to 5 units in its length. What is the length of the missing side? Side CB. For the drawing, it is very easy to see that CB equals to NB minus NC. Again, NB minus NC equals to CB. So I write it down. CB equals to NB minus CB. CB equals to NB minus NC. NB minus NC. So CB equals to NB, that is 5. NC minus NC. NC equals to 2 units in its length. So in total CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. In the next step, we will do another construction, that is to say, from point A, we will draw perpendicular on side CB. Again, from point A, we will draw perpendicular on side CB. We will define the touching point of the perpendicular from point A and CB. This point is point O. We will define the length of side AO as H. So from point A, we draw perpendicular to CB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. In the next step, I'll copy the green right triangle A or B in a new page, and we will find out the length of side AO, that is equals to H. So actually, this is the right green triangle, triangle A or B, that is coming from the original drawing. This triangle A, the right triangle A or B, sinus 60 degrees equals to AO over AB. So I'll write it down. Sinus 60 degrees equals to AO over AB. AO is H, according to our definition, over AB. AB is 5, according to what is given as the question. So in total, we can find out that sinus 60 degrees is equal to H over 5. Sinus 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we will multiply this equation by 5 and finally get that H equals to 5 times square root of 3 over 2 units in its length. So H equals to 5 times square root of 3 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of the green triangle, triangle ABC? We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. Repeat again, the area of any triangle equals to the base of the triangle times the height to the base over 2. We will choose the base of this triangle ABC as CB, and the height must be equal to h. Why the height is h? Because it creates 90 degrees with the base CB. Okay, so therefore the area of this triangle, triangle ABC, must be equal to the base CB times the height h over 2. Then again, the area of the green triangle ABC must be equal to the base CB times the height h over 2. CB equals to 3 units in its length. And just right now found out that h equals to 5 times square root of 3 over 2 units in its length. And we have to divide it by 2. All divided by 2. So in total, in the numerator of this expression, we have 3 times 5, that is 15, times square root of 3, over 2 times 2, that is 4. So if we found out that the area of this green triangle, triangle ABC, it is equal to either 15 times square root of 3 over 4 square units in its size. In terms of numbers, the value of this expression, it is actually 6.5 square units in its size. Repeat again, I should found out that the area that we are looking for this question, that is the area of this main triangle, triangle ABC, it is equal to either 15 times square root of 3 over 4 square units in its size. In terms of numbers, the area of this triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. Point O is the center of this semicircle. This is line segment PO that is equal to 10 units in its length. This is line segment QP that is equal to 21 units in its length. Here QP equals to 21 units. And again, line segment QP equals to 21 units in its length. This is called QS, this is equals to 16 units in its length. This is angle PQS, that is a right angle. Again, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So first of all, we will complete this semicircle to a circle. So actually completed the semicircle to a circle, and we will extend line segment QP by side line until it touches the circle. And we define the touching point of the standard isomet QP with this circle. This point is point M. In the next step, we will join points S and M together by a straight line. Point O is the center of this circle. So by doing all those constructions, we created peripheral angle SQM, that is a right angle according to what is given as a question. So peripheral angle SQM equals to 90 degrees in its size, and peripheral angle SQM subset on chord SM. Again, peripheral angle SQM subset on chord SM. So here we can implement rule 5. Repeat quickly on rule 5. According to rule 5, any peripheral angle that is equals to 90 degrees must subset on the diameter of the circle. In the moment we have a circle, this is peripheral angle MAN that is equals to 90 degrees in its size, and according to this rule 5, any peripheral angle that is equals to 90 degrees in its size must subset on the diameter of the circle. And indeed, peripheral angle MAN, that is a right angle, subset on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equals to 90 degrees in its size must subset on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle MQS, that is a right angle according to what is given as the question, and therefore according to rule 5, peripheral angle MQS must subset on the diameter of the circle. Peripheral angle MQS subset on chord SM, and therefore according to rule 5, chord SM must be the diameter of this circle. So write it down. If you found out that chord SM is the diameter of this circle according to rule 5. Point O is the center of this circle, point S is the point on the circle itself, therefore OS must be the radius of this circle. We'll define the radius of this circle as R, so OS equals to R. Likewise, OM is also the radius of this circle, therefore it is equal to R units in its length. In the next step, we will do another construction. That is to say, from point O, that is the center of this circle, we will do perpendicular on QP. Again, from point O, we will do perpendicular on QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and QP. This point is point N. In the next step, we will focus on the big right angle, triangle SQM. So in the big right angle SQM, this is the big right angle SQM. We will define this angle, angle QMS, as alpha. So in the right triangle SQM, this angle equals to alpha. This angle equals to 90 degrees. And therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will focus on the small right triangle, triangle O and M. The small right triangle O and M, we have this angle that is alpha. Actually, angle alpha is a common angle that belongs to both triangles. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. it is very easy to see that the big right triangle SQM is similar to the small right triangle, triangle ONM, according to angle similarity rule. So I will explain anyway why the big right triangle SQM is similar to the small right triangle, triangle ONM. First of all, this is angle alpha. That is a common angle that belongs to both triangles. So we can write out that angle alpha equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if we found out that all the figures of the big right triangle SQM are correspondingly equal to all the figures of this small right triangle, triangle ONM. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle, triangle ONM, according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle, triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle, triangle SQM. Okay, again, we will derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is. Over SQ equals to 16 units in its length according to what is given as the question. And it is equals to OM. OM is the radius of this circle, that is equals to R over SM. SM is the diameter of this circle, that is equals to 2R. So in total, if you found out that ON over 16 equals to R over 2R. Here, R is the numerator and R is the denominator, so R will get cancelled. So we cancelled R, we left in this side of the equation only with 1/2. That is equal to ON over 16. Or ON over 16 equals to 1/2. Here we will multiply this equation by 16 and finally we get that the missing side ON is equal to 16 over 2, that is 8. So if you found out that this is the missing side ON, that is equal to 8 units in its length. In the next step, I'll copy the right small green triangle, triangle ONP, in the new page, and we will implement the Pythagoras theorem on this small white green triangle, triangle ONP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a expression for Pythagoras theorem. The hypotenuse PO for the right triangle PNO is equals to 10 units in itself, according to what is given as the question. PN is the missing side, and just like I found out that side NO for the green triangle PNO is equals to 8 units. So actually, this is the small green triangle PNO that I got it from the original drawing. This right triangle PNO according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. Okay, again, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to Pn squared. Pn is the missing side, so we leave it as it is. This is Pn squared plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we found out that 100 equals to Pn squared plus 64. Here we subtract 64 from this equation, and we get that Pn squared equals to 100 minus 64 is 36. So Pn squared equals to 36. Here we take a root out of this equation and finally get that the missing side Pn equals to the square root of 36, that is 6. So she found out that the length of this missing side Pn is equal to 6 units. What is the length of the missing side Qn? From the drawing, it is very easy to see that Qn equals to Qp minus Np. Again, Qp minus Np equals to Qn. So I write it down. Qn equals to Qp minus Np. So Qn equals to Qp equals to 21 units in itself, according to what is given as the question, minus Np. Np equals to 6 units, according to what we already found out. So in total Qn equals to 21 minus 6, that is 15. Qn equals to 15 units in its length. This is 97 Qn, that is equals to 15 units in its length. In the next step, we join points O and Q together by a straight line. Point O is the center of this circle, point Q is the point on the circle itself, therefore OQ is the radius of this circle, that is equals to R according to our definition. In the next step, I'll copy the white triangle Q and O in a new page, and we'll implement on this white triangle Q and O the Pythagoras theorem. Here by PT is a relation for Pythagoras theorem. So actually, this is the right triangle Q and O that are going from the original drawing. This right triangle Q and O, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So I write it down. QO squared, that is the square of the hypotenuse, is equal to Qn squared plus On squared. The hypotenuse QO is also the radius of the circle that is equals to R. QO equals to R, therefore QO squared equals to R squared. And it is equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225, plus On squared. On is 8, therefore On squared is 8 squared, that is 64. So total we found out that R squared equals to 225 plus 64, that is 289. So she found out that R squared equals to 289. Here we will take a root out of this equation and finally get that the radius R of the circle is equal to the square root of 289, that is 17. So she found out that the radius R of this circle is equal to 17 units in its length. The radius R equals to 17 units in its length. We know that OA is also the radius of this circle is equals to R. So AO is also the radius of this circle. Is equals to R according to our definition. From one side, OA equals to the radius of the circle, that is R. But from the other side, AO also equals to AP plus PO. Again, AO equals to AP plus PO. So you can write down that AO equals to AP plus PO. But AP itself equals to X. AP is the line segment that we are looking for in this question. And it is equals to X plus PO. PO equals to 10 units in its length according to what is given as the question. Repeat again. AP equals to X and PO equals to 10 according to what is given as the question. And from this long equation, we will derive that 17 equals to X plus 10. 17 equals to X plus 10. Here we subtract 10 from this equation. And finally we get that X equals to 17 minus 10, that is 7. So if you found out that AP that is equals to X is equal to 7 units in its length. And that is the answer to the question. I'll repeat again. If you found out that the short line segment AP is equals to X is equal to 7 units in its length. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our test was to find out the area of this green triangle, triangle ABC. So, in the drawing, we have the big quadrilateral QABCP. In addition, it is given us the question that side AQ equals to side AC. And therefore, triangle ACQ is an isosceles triangle, and QC is the base of this isosceles triangle, triangle ACQ. Repeat again. Triangle ACQ is an isosceles triangle, and QC is the base of this isosceles triangle, triangle ACQ. In addition, it is given in the question that this is angle QPC, that is equals to 16 units in its length. This is angle PQC, that is the right angle. This is angle ABC, that is also equals to 16 units. So this is angle ABC, that is also equals to 6 units in its size. This is line segment PC, that is equals to 4 units in its length. And this is side AB, that is equals to 5 units in its length. Again, our test is to find out the area of this green triangle, triangle ABC. So in the first step we did a construction, that is to say, from the vertex A of the associated triangle ACQ, we draw perpendicular on the base QC. Again, from the vertex A of the associated triangle ACQ, we draw perpendicular on the base QC. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and the base QC. This point is point M. So here we can implement rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So in our drawing, we can implement rule 22 in our drawing. Why? In our drawing, we have the perpendicular AM to the base QC. And according to rule 22, the perpendicular AM to the base QC of the associated triangle ACQ bisect the base QC. That is to say, the perpendicular AM divides the base QC into two halves. The first half is QM and the second half is MC. And of course the first half, QM, must be equal to the second half MC. So if we define the length of the first half QM as A, then the second half MC must be also equal to MC instead, because they are equal to each other. In the next step, we extended the perpendicular AM by straight line until it touches line 7 PC. We define the touching point of the extended perpendicular AM with line 7 PC. This point is point M. So AM is a perpendicular, it is absolutely a straight line. Then we extended the straight line AM by straight line. When you extend the straight line by straight line, the result AN must be also a straight line. So AN must be also a straight line. And if you focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have? The right side of the straight line AN at point M. We have this angle that is the right angle, plus this missing angle. We told that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the right angle PQC, 90 degrees plus 60 degrees is 150 degrees. So 150 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle MNC, 30 degrees plus 90 degrees is 120 degrees. So 120 degrees plus the size of this third missing angle in total must be equal to 180 degrees according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. And therefore, this third missing angle must be equal to 60 degrees in its size. Triangle, the right triangle PQC is similar to the small right triangle NMC according to angle similarity rule. That is to say, this is angle C that equals to 30 degrees in its side. Angle C is a common angle that belongs to both triangles. So we can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So we should find out that all the figures of the right triangle PQC are corresponding equal to all the figures of the right small triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So if again, I should find out that the right big triangle PQC is similar. This is the sum of similar to the right small triangle NMC according to angle similarity rule. And from the fact that the right big triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We derive that side NC, of the small right triangle NMC, or side PC of the right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. Repeat again. We derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equals to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we limit the CTs over PC. PC equals to 4 units in itself according to what is given in the question. And it is equals to MC. MC equals to A units in itself according to our definition over QC. QC equals to A plus 8, it is 2A. So in total we found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation we have to leave with 1 half, that is equals to NC over 4, or NC over 4 equals to 1 half. Here we multiply this equation by 4, and we found out that the missing side NC is equal to 4 over 2, that is 2. So this is the missing side NC, that is equals to 2 units in its length. In the next step I copy the big triangle A and B in the new page and analyze this big triangle NAB. This is the big triangle A and B, that is copied from the original drawing. Side AB equals to 5 units in its length according to what is given in the question. Here we have 60 degrees plus 60 degrees is 120 degrees. So 120 degrees plus the size of this third missing angle, in total it must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. And therefore this third missing angle must be equal to 60 degrees in its size. So all the angles in the big triangle A and B are equal to each other. Therefore triangle A and B is an equilateral triangle. And we know that all the sides of any equilateral triangle are equal to each other. AB equals to 5, therefore A must be also equal to 5, and B must be also equal to 5 units in its length. So actually this is side NB that equals to 5 units in its length. What is the length of the missing side CB? From the drawing it is very easy to see that CB equals to NB minus NC. Again, CB equals to NB minus NC. So CB equals to NB, that is 5, minus NC, that is 2. So in total CB equals to 5 minus 2, that is 3. This is the missing side CB, that equals to 3 units in its length. So in the next step we did the construction, that is to say from the vertex A of the great triangle ABC, we draw perpendicular on CB. Again, from the vertex A, we draw perpendicular on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and side CB. This point is point O. We define the length of side AO as H. In the next step, I copied the right great triangle AOB in a new page, and we found out the length of side AO that is equals to H. So actually, this is the right great triangle AOB that I copied from the original drawing. In this right triangle AOB, sin of 60 degrees equals to AO over AB. Again, sin of 60 degrees equals to AO over AB. AO is H, AB is 5. So in total, sin of 60 degrees equals to H over 5. Sin of 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we multiply this equation by 5 and finally found out that H equals to 5 times square root of 3 over 2 units in its length. AO that is equals to H is equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle ABC. We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. Okay, again, the area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base of this great triangle ABC as CB. So it is CB times the height. The height is H because it's 90 degrees with the base CB. So the height is H over 2. So if we found out that the area that we are looking for in this question, that is the area of the great triangle ABC, it is equals to the base CB times the height H over 2. CB is 3 times the height H. H is 5 times square root of 3 over 2. So it is 3 times 5 times square root of 3 over 2. That is 8, and we have to divide it by 2. So in total, in the numerator of this expression, we have 3 times 5, that is 15 times square root of 3, over 2 times 2, that is 4. So we found out that the area of this green triangle ABC is equals to either 15 times 4 to 3 over 4 square units in its size. In terms of numbers, the value of this expression is 6.5. But again, we found out that the area of this green triangle ABC is equals to either 15 times 4 to 3 over 4 square units in its size. In terms of numbers, the area of this green triangle ABC is equals to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of the semicircle. In addition, we know that this is line segment PO that is equals to 10 units in its length. This is line segment QP that is equals to 21 units in its length. This is called QS that is equals to 16 units in its length. This is angle PQS, that is a right angle. Again, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So first of all, we completed this semicircle to a circle, and we extended line segment QP by a straight line until it touches the circle. We define the touching point of the extended line segment QP with the circle. This point is point M. In the next step, we join points S and M together by a straight line. By doing all those constructions, we created here peripheral SQM. This is peripheral SQM, that is a right angle according to what is given as the question. So here we can implement rule 5. According to rule 5, any peripheral angle that is equals to 90 degrees in its size must subtend on the diameter of the circle. So in our drawing, we have peripheral SQM that is equals to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. Peripheral SQM subtend on SM, on chord SM, and therefore according to rule 5, chord SM must be the diameter of the circle. Chord SM is the diameter of the circle according to rule 5. So point O is the center of the circle, point S is the point of the circle itself, therefore OA must be the radius of the circle. We define the radius of this circle as such, so OS equals to R. Likewise, OM is also the radius of the circle, therefore it is equals to R. In the next step, we did the construction, that is to say, from point O, that is the center of the circle, we do perpendicular on QP. Again, from point O, that is the center of the circle, we do perpendicular on line segment QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. In the next step, we focused on the big right triangle SQM. The big right triangle SQM, we define this angle as alpha. So this angle equals to alpha. This angle equals to 90 degrees, and therefore this 5 angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the small right triangle O and M, this angle equals to alpha. Therefore, angle alpha is a common angle that belongs to both triangles. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. In the next step, we prove that the big right triangle SQM is similar to the small right triangle O and M according to angle similarity rule. That is to say, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the triangles of the big right triangle SQM are corresponding equal to all the triangles of this small right triangle ONM. And therefore those two right triangles are similar to each other according to angle similarity rule. So if you found out that the big right triangle SQM is similar, this is the sum of similar to the small right triangle ONM according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equals to side OM of the small right triangle ONM over side SM of the big right triangle SQM. So repeat again, we will derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equals to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is, over QS. QS equals to 16 units in itself, according to what is given the question. And it is equals to OM. OM is the radius of the circle, is equals to R, according to our definition. OM equals to R over SM. SM is the diameter of the circle according to rule 5. And therefore it is equals to R plus R, that is 2R. SM equals to 2R. So in total, if you found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. And in this side of the equation, we left only with 1 half. That is equals to ON over 16, or ON over 16 equals to 1 half. Here we multiply this equation by 16 and found out that the missing side ON equals to 16 over 2, that is 8. So here this is the missing side ON, that is equals to 8 units in its length. In the next step, I copied the right small green triangle O and P in a new page, and we implemented the Pythagoras theorem on this small right green triangle O and P. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares for the perpendiculars. So actually this is the right green small triangle O and P that I copied from the original drawing. This small green right triangle O and P, P all squared, that is the square of the hypotenuse, equals to ON squared plus PN squared. Or P all squared equals to PN squared plus NO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to Pn squared. Pn is the missing side, so we leave it as it is, plus On squared. On is 8, therefore On squared is 8 squared, that is 64. So in total, we found out that 100 equals to Pn squared plus 64. Here we subtracted 64 from this equation. And finally, we found out that Pn equals to 100 minus 64 is 36. So Pn squared equals to 36. Here we took a root out of this equation and found out that the missing side Pn equals to the square root of 36, that is 6. So this is the missing side Pn, that equals to 6 units in its length. What is the length of this missing 9 segment Qn? From the drawing, it is very easy to see that Qn in total equals to Qp minus Np. Again, Qp minus Np equals to Qn. Qn equals to Qp minus Np. So Qn equals to Qp, that is 21, according to what is given as a equation, minus Np, that is 6, according to what we just right now found out. So Qn in total equals to 21 minus 6, that is 15. So this is the missing 9 segment Qn, that is equals to 15 units in its length. In the next step, I copied the right triangle Q and O in your page. Actually, we join points Q and O together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore QO is the radius of this circle, that is equals to R. In the next step, I copied the right triangle Q and O in the new page, and we implemented the Pythagoras theorem on this right triangle Q and O. So actually, this is the right triangle Q and O that I copied from the original drawing. In this right triangle Q and O, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. Again, QO squared equals to QN squared plus ON squared. QO is R, therefore QO squared is R squared. This equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225, plus On squared. On is 8, therefore On squared is 8 squared, that is 64. So in total, R squared equals to 225 plus 64. 225 plus 64 is 289. So in total, we have found out that R squared equals to 289. Here we took out of this equation and found out that R, the radius of the circle, equals to the square root of 289, that is 17. So the radius of this circle R equals to 17 units in its length. The radius R equals to 17. But AO is also the radius of the circle. Again, AO is also the radius of the circle, so here, AO is the radius of the circle, that is equals to 17 units in its length. From one side, AO is the radius of the circle. But from the other side, AO also equals to AP plus PO. So we can write down that AO equals to AP plus PO. But AP is the line segment that we are looking for in this question, and it is equals to X. And PO equals to 10. Again, AP equals to X and PO equals to 10 units in its length, according to what is given us the question. From this long equation, we will derive that 17 equals to X plus 10. Again, 17 equals to X plus 10. 17 equals to X plus 10. Here we subtract 10 from this equation. And we found out that X equals to 17 minus 10, that is 7. So X equals to 7 units in its length. That is to say, the length of the short line segment AP that is equals to X is equal to 7 units in its length. So the answer to the question is the length of this short line segment AP is equals to X is equal to 7 units. Okay, then thank you very much.